Ms. Berg, the science quirk. Berk, 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 Berk. Ms. Berg, she makes you work. Berk, 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 Berk. Science is cool. This is Physics, Chapter 4, Section 4. This is our final section in this chapter. That means once we finish our labs, we'll be ready to take our test on forces. Today we'll be talking about everyday forces. And one of our objectives will explain the difference between mass and weight. Hopefully you'll know what that is because we've been discussing it since 8th grade physical science. We also want to find the direction and magnitude of normal forces. We'll describe air resistance as a form of friction. Did you know that air resistance is friction due to air? And then we'll use the coefficients of friction to calculate the frictional force. All right, so first, what is weight versus mass? Well, weight is the gravitational force that is exerted on an object by the Earth. And it is a vector quantity directed towards the center of the Earth. The magnitude of this force, we're going to call it force F sub g, is a scalar quantity that we call weight. And weight will change with the location of an object in the universe. So, for example, if we get your weight here on Earth, which is your mass times the acceleration of gravity of the Earth, which is 9.81 meters per second squared, you will come up with a weight in newtons. However, if you go on the moon has a much smaller gravitational pull. Your weight will be far less. And if you go in outer space, you'll be virtually weightless and float around. So that's what they mean by weight changes. Your mass, however, doesn't change. You don't get less mass by going in outer space, just less weight. So calculating a weight at any location would be the mass of the object times the acceleration due to the gravity at that location, or the free fall acceleration at that location. In the case of being close to the Earth's surface, it's 9.81 meters per second squared. Let's watch a visual concept.
The mass of an object depends on the amount of matter the object contains. As long as the amount of matter remains constant, so does the mass of the object. The weight of an object depends on the force gravity exerts on it. Therefore, if the force of gravity on an object changes, so does its weight. The weight of an object depends on gravity. Changing an object's location will change its weight. For example, consider an astronaut who has a mass of 80 kilograms. On Earth, this astronaut weighs 784 newtons, but on the moon's surface, where the force of gravity is only 1.6 meters per second squared, the astronaut weighs 131 newtons. The astronaut's mass, however, remains the same on Earth or the moon. Weight can be measured using a spring scale. The spring scale measures the force exerted on an object by gravity. The weight of an object is expressed in newtons. Mass is measured using a balance. A balance uses a comparative mass on a lever arm to determine the mass of an object. The mass of an object is expressed in kilograms.
Okay, so you use a balance to measure mass, and you use a scale, a spring scale, to measure weight. So, what is a normal force? A normal force acts on a surface in the direction that is perpendicular to the surface. The normal force is not always opposite in direction to the force due to gravity. For example, remember the duck problem where he slid down the incline? That was perpendicular to the incline. So here's an example also. In the absence of other forces, the normal force is equal and opposite to the component of the gravitational force that is perpendicular to the contact surface. There's the key there, perpendicular to the contact surface. In this example, our F sub n, or our normal force, would be the mass times acceleration due to gravity times the cosine of theta, where theta is the angle of the incline. And also notice that the same angle then perpendicular or normal to the force, that would also be theta. Let's look at our visual concept.
When talking about forces, the word normal means perpendicular, and it always indicates the direction that is perpendicular to the surface of contact between two objects. Consider an object resting on a flat surface. The external force of gravity is acting on the object. The object is not moving down, so there must be another external force acting on it. This is the reaction force of the surface on the object. In this case, the normal force is exactly opposite to the force of gravity, but as the inclination of the surface of contact changes with respect to the ground, the normal force is no longer in the exact opposite direction of the force of gravity.
Okay, so it's perpendicular to the surface. So notice as you raise the incline, it's still perpendicular to the surface. All right, now let's talk about friction. Static friction is a force that will resist the start or the initiation of a sliding motion between two surfaces that are in contact and at rest. We have a lot of practice with friction. If you want to increase friction, you would put spikes on your feet for, say, baseball or football, where you have cleats that dig in and increase the friction between the shoes and the surface. If you want to reduce friction, you may smoothen a surface or sharpen an edge like ice skates on ice to make less friction. Kinetic friction is the force that opposes the movement of two surfaces that are in contact and sliding over each other. So static friction and kinetic friction are similar in the sense that it's the force that resists motion. Static is the initial motion to get something moving. It could be greater than the actual friction, and usually is, of the friction once that force is in motion. So kinetic friction, notice, is always less than the maximum static friction.
Friction makes it more difficult to move an object across the surface of another object. Surface texture, electrical attraction, and other forces that push objects together all affect the friction experienced by the objects. Even if the surfaces of two objects appear to be smooth, they are rough on a microscopic level. In general, as the roughness of a surface increases, the friction increases, and more force is required to move the object along a surface. Even the surface of fluids, such as water and air, can cause friction. The reason swimming provides such a good workout is that you must exert force to overcome the friction created by water molecules. Electrical attraction also plays a role in friction. Pushing a strong magnet across a refrigerator door requires more force than pushing the same magnet across a wooden table. The greater the attraction pushing the objects together, the more the objects resist movement, and the greater the friction. On the other hand, if the electrical attraction is negative and the objects repel one another, friction can be reduced. Maglev trains take advantage of this phenomenon to give a smooth, nearly frictionless ride. Forces such as gravity can also push objects together. The heavier the object being moved across a flat surface, the greater the friction due to its weight. Similarly, if we push down when moving sandpaper across a piece of wood, we increase the force pushing the surfaces together, and consequently increase the friction.
Makes common sense. Right, so now let's talk about friction forces in free body diagrams. How would we show those? In free body diagrams, the force of friction is always parallel to the surface of contact. So the force of kinetic friction is always opposite of the direction of motion. To determine the direction of the force of static friction, we'll use the principle of equilibrium. So for an object in equilibrium, the friction force must point in the direction that results in a net force of 0. So let's look at the coefficient of friction. That is the quantity that is expressed in the dependence of frictional forces on a particular surface in contact, that it's in contact with. That is called the coefficient of friction, and they use the Greek letter mu for that coefficient. The coefficient of kinetic friction, we'll say mu sub k for kinetic, equals force of the kinetic force divided by the force of normal. The coefficient of the static friction, we'll use mu sub s equals the force exerted statically, or the maximum force exerted divided by normal. So what kind of coefficients are we looking at? If we're looking at steel on steel, the maximum kinetic friction force to get steel on steel moving is 0.74 newtons, and this coefficient of friction is 0.57. So you see that the kinetic, if one steel is moving, is much lower. Notice again, aluminum on steel is higher statically than it is once it's in motion. Rubber, pretty close together there. Rubber on wet concrete, virtually non-existent versus 0.5, and so on. Notice it's always higher than lower, higher than lower, higher than lower, higher than lower. Let's talk about a sample problem about overcoming friction. So here's our problem. We have student, I can't even tell if it's Molly. I was going to say Molly. Attaches a rope to a 20-kilogram box of books. Oh, it's a he. So he pulls with a force of 90 newtons. At an angle, notice, see the angle of the rope is kind of an upward angle. The angle's at 30 degrees with horizontal. The coefficient of kinetic friction, that means once the box is in motion, is 0.5. Let's find the acceleration of the box. Let's first define what is given. So we know the mass of the box is 20 kilograms. We know that he's applying a force of 90 newtons at 30 degrees, and we know our coefficient of kinetic friction is 0.5. What do we need to know? Our acceleration. Well, what's our equation? Force equals mass times acceleration, correct? Well, let's look at our forces that we have in a free body diagram. The force applied is at that 30-degree angle. So you see the F applied, that is the rope. We have the force of gravity going down, and that's our 20.0 kilograms times 9.81 meters per second squared. Normal is pointing up in the opposite direction, and our force due to friction is F sub k, and that's a kinetic force due to friction. Notice it's pointing in the opposite direction of the applied force of him pulling on the rope. All right, so first we need to choose a convenient coordinate system. So remember last time we said the most number of forces that will lie exactly on the x and y coordinate planes, that's where you want to choose your coordinate system. So here we show our force of gravity and our force of normal, and then our friction force. We can get all three of those lying on the xy coordinate. So we only have the force of applied to do some trigonometry too. So here's our diagram showing the most convenient coordinate system, and we only need to resolve the f applied into our x and y coordinates. So in order to do that, to find the force in the y direction, we would take the 90 newtons that he's applying on the rope times the sine of 30 degrees, and that would be 45 newtons pull upward. And then when he takes the 90 newtons times the cosine of 30 degrees, we'd find that he was also pulling 77.9 newtons to the right. So we want to find the normal force by applying the equilibrium in the vertical direction. And then we know that that would be 0, and we calculate the force of kinetic friction on the box by taking the force of kinetic friction times the coefficient of friction times normal. So then we apply Newton's second law along the horizontal direction to find the acceleration of the box. Of force, the sum of the forces equals the mass times the acceleration. And in this case, it's the sum of the forces on the x-axis times the mass times acceleration in the x-axis. So in order to apply the condition of equilibrium in the vertical direction, we also need to account for all the forces that are in that vertical y direction. So we have the force of gravity, we have the force of normal, and we have the force that's applied in the y direction. So we already know the force that's applied in the y direction, and we can use the box's mass times gravity to find F sub g. So the force applied y we calculated already as 45 newtons, and there's our 9.81 times the mass of the box of 20.0 kilograms, and we have 196 newtons. Next, we'll apply the equilibrium condition of the summation of the forces in the y direction is 0. So let's resolve for normal. So the summation of the forces in the y direction is the normal force plus the applied y force, and subtract the force of gravity, and they must add up to 0. So if they add up to 0, and we don't know the normal force yet, we do know that the applied force we calculated was 45 newtons. We subtract the force of gravity of 196 newtons, and we find that our normal force then must be 151 newtons. So remember, pay attention to the direction of the forces. So F sub g is subtracted from F of n, and the applied y force, because the force of gravity, or F sub g, is downward. So that's why it's subtracted from it. All right, so now we'll use the normal force to find the force of the kinetic friction. So you have our coefficient of 0.500 times our force of normal of 151 newtons, and we get our force of friction of 75.5 newtons. We're still not done. Now we need to use Newton's second law to determine the horizontal acceleration, because we want to know how fast is the box going to accelerate. So we take the summation of the forces in the x direction, which is our force applied minus the force of friction, and that'll equal our mass times acceleration. Well, if we plug in our numbers, our applied force in the x direction we calculated was 77.9, and we most recently calculated up above there in step B, our force of kinetic friction of 75.5. We subtract those and divide by mass, because force equals mass times acceleration. We're solving for acceleration. And you come up with the acceleration of the box is 0.12 meters per second squared to the right. So let's look at it. The box accelerates in the direction of the net force along the lines of Newton's second law. The normal force is not equal to the in magnitude to the weight, because the y component of the student's pull helps the support of the box, because he's actually pulling up on the box. Now let's talk about air resistance. Air resistance is a form of friction. So whenever an object moves through a fluid medium, such as air or water, the fluid provides a resistance to the object's motion. In fact, they have classes on this called fluid dynamics. For a falling object, when the upward force of air resistance balances out the downward gravitational force, the net force of the object is zero, and the object then that would continue to move downward with a constant maximum speed. When it reaches a maximum speed, that's called its terminal speed. You may have heard it called terminal velocity before. Okay, so what are fundamental forces? There's 4 of them. We have electromagnetic force, we have gravitational force, we have a strong nuclear force, and we have a weak nuclear force. So these are the 4 fundamental forces that we call field forces. And we are done with today's lecture.